Hey class, Adam Ward here. I want to talk to you today about mixed flow reactors. This is content that's associated with Lecture 9 in your textbook. In preparation for this lecture, you should have watched me talk to you about plug flow reactors, or reactors that include advection only. And so when we talk about a mixed flow reactor, think of this as a plug flow reactor plus. So we're taking everything that we've done before, we're simply adding terms to describe diffusion or dispersion. And so I want to take a look at what we think this might look like in terms of a steady state profile. And so if you can envision that there was a load dripping into this mixed flow reactor at this red plane that I've drawn, in the downstream direction you've got not only advection, but you've also got dispersion helping spread this out. One interesting thing that comes up in mixed flow reactors, however, is that you get dispersion in the upstream direction, meaning some mass can propagate upstream or sort of move against the dominant advective flow through its own mixing processes. And so you will get some concentration migrating upstream of that load. Now, what does our general equation look like? This is our advection dispersion equation that we drew out before. And you notice I've got a first order reaction term in there as well, that minus Kc. And so we'll go ahead and apply this general equation to a couple of problems here. Mixed flow reactor response to a point source. We've got both advection and diffusion. And so the response here for x is greater than 0. And again, that's important because on the x greater than 0 side, you've got advection and dispersion working together to move mass in the downstream direction. That equation can be simplified, and you can come up with an exact solution that's written here. Now, it looks something like our previous general solution. We've got that C naught, or the concentration at the well-mixed point, times e to the u over 2e, so you see velocity and dispersion showing up there. Times the quantity 1 minus the square root of 1 plus 4 times nu, and then an x. So that's a lowercase nu, looks like a squiggly n, and that's what we call an estuary number. Estuary number is calculated as that first order reaction rate coefficient k times our dispersion coefficient divided by velocity squared. And so you can think about this as describing what's more dominant in the problem. And so if n is greater than 1, that means the top part of that is greater than the bottom portion, or diffusion is greater than advection. Suggests to us a diffusion-dominated system. If it is less than 1, that suggests the denominator is bigger, and this is an advection-dominated system. In your textbook, Chopper gives you some advice about when you could ignore one or the other. And so, for example, how little diffusion is meaningful before we just use a plug flow reactor. And if I remember correctly, he uses 10 and 0.1 as the thresholds. So if your estuary number is greater than 10, treat it like it's a diffusion-only problem. If it's less than 0.1, treat it like it's an advection-only or a plug flow reactor problem. Now, that equation was for x is greater than 0, so downstream of the load. Upstream of the load, you've got almost an identical equation. In fact, the only difference here, as I'm pointing out with the purple, is that you go from having a minus sign to a plus sign in that numerator, or in the exponent, excuse me. So this is mixed flow reactors responding to a point source at steady state. What is this going to look like? And so here is, again, a plan view of a river and then a plot of concentration through distance. At x equals 0, we'll have some peak concentration, which will decay as you move both in the positive x and the negative x directions. One additional equation that's useful to you: how do you calculate that C naught right at the point of mixing? We previously used end member mixing. End member mixing doesn't work here because it's not simply mixing instantaneously. As soon as it mixes, you get dispersion instantly starting to move mass in both directions. So to solve this problem, C naught we can calculate as the mass rate that's being loaded, W, divided by Q times the root of 1 plus 4 times nu, or 4 times our estuary number. We'll also look at a distributed source. In this case, Chopper describes these as an inflowing concentration and a length over which that inflow occurs. And the equation that we solve, Chopper presents to you, is a sum of two exponentials, f times e to the lambda 1x plus g times e to the lambda 2x. Graphically, the solution looks like what I've drawn here. Again, I want to point out to you, upstream of x equals 0, there is a little bit of tailing because dispersion is moving mass in the upstream direction. Otherwise, the solution downstream of x equals 0 looks an awful lot like what we did for a plug flow reactor with a distributed source. I'll go ahead and write out what these terms are. Again, not something to memorize, these are something to look up. And so lambda 1 and lambda 2 are just coefficients that look an awful lot like what we used to have in the exponent for just a point source into a mixed flow reactor. Notice here the signs are different for lambda 1 and lambda 2. F has a fairly complicated equation. G looks just like F, but switching lambda 1 and lambda 2 around. So everywhere there was a 2 in the F equation, you put a 1 in the G equation, and so forth. So, do I want you to memorize this? Absolutely not. Do you have to know that it's lambda 2 or lambda 1 and you switch it? Absolutely not. You can look up these equations when you need them. What I want you to understand is that you have exact solutions for this problem, and I want you to be able to conceptually draw out what these concentration through distance profiles would look like. Finally, I want to talk to you just briefly about a couple of other numbers. In this lecture, the estuary number came up, and that let us differentiate between advection-dominated and dispersion-dominated systems. But there are a few other numbers that you may see come up in your career or as part of the given information for a problem. The first is the Peclet number, and this is length times velocity divided by the dispersion coefficient. And this ends up being a completely unitless number, so all of your units ought to cancel out. And the idea here is that you're comparing the rate of advective transport to the rate of diffusive transport. So how much faster is advective transport than if this were a dispersion-only system, or vice versa? So that lets you compare between two processes. The idea partly behind these unitless numbers is that they also let us compare between systems. So we can collapse a whole variety of very heterogeneous systems with fast and slow transport, short and long study reaches, high and low diffusion coefficients into perhaps one plot of what explains transport as a function of its Peclet number. The other number that comes up oftentimes in my own research as well as in your careers is a Domkohler number. And the idea of a Domkohler number is comparing rates of reactions to rates of transport. And so in particular, as presented in your textbook, we look at the rate of consumption. So how fast is the concentration we're interested in decaying as it moves through the system, and compare that to the rate of advection. So a high Domkohler number tells you that there'll be a lot of consumption relative to transport, or the chemical reaction might dominate over the physical processes. A very low Domkohler number suggests to you that it's an advection-dominated system and there's very little consumption, meaning very little uptake or very little removal of your constituent due to that reaction. So these are a couple more ways that we try to boil down systems into summary statistics, if you will, that help us understand what processes really matter, what processes might we be able to simplify. All right, class, I hope this helps. When I see you on Thursday, we'll go ahead and do a couple of lecture problems related to mixed flow reactors. Thanks, all.